Now it is better to name the paths. AB, FC, ED. Now I am drawing the path from AF, CBA. AF, CBA. A to A via FCB. So see the direction. I1, this I1 into small r1 plus I1 into capital R1 plus I1 plus I2 into capital R plus I1 into R3 is equal to EMF 2 volts. What is small r1? Internal resistance of 1 ohm. And what is R2? Internal resistance of 2 ohms. Let me substitute these values and equate to E1. So I1 into small r1 is equal to 1 ohm plus I1 into what is capital R1? 5 plus what is I1 plus I2? I1 plus I2, okay. This what is capital R? 10 plus I1 into what is R3? 2 ohms is equal to, with this loop means in the path of AF CBA is equal to the E 2 ohms, 2 volts. So therefore please simplify this equation. This is I1 plus 5I1, 6I1 plus 10I1, 16I1 plus 2I1, 18I1 plus how many I2s are left? Plus 10I2 is equal to 2 volts. Simplify this equation. 9I1 plus 5I2 is equal to 1 volt. Give an equation number to this one. So for this path we have got an equation 9I1 plus 5I2 is equal to 1 volt. What is the another path of the circuit? See this one. Some FE DCF. FE DCF. In this path we will get the same type of equation and we will solve these two equations. We will get the I value and V value. Next path is CDEFC. CDEFC. So what is the direction? Yeah, see. I2 into small r2 plus I2 into capital R2 plus I1 plus I2 into R plus I2 into R4 is equal to E2. So what is this path? CDEFC. Now we will substitute the small r2, capital R2 and R and R4 values and E2 values in the equation. So what is the small r2? 2 ohms. Therefore I2 into 2 plus I2 into what is capital R2? 5 ohms plus I1 plus I2 into what is capital R? 10 ohms plus I2 into what is capital R4? 2 ohms. What is E2? E2 is 1 volt. So it is 2I2 plus 5I2 plus I1 plus I2 into 10 plus 2I2 is equal to 1 volt. If you substitute all these things, 2 plus 5, 7, 7 plus 2, 9, 9 plus 10, 2 plus 5, 7, 7 plus 2, 9, 9 plus 10, 19. Therefore, it is 19I2 plus 10I1 is equal to 1 volt. This is equation 2. Now, we will solve the equation 1 and 2 Therefore, we will get the I1 and I2 values and V values. The two equations, 9I1 plus 5I2 is equal to 1. Second one, 10I1 plus 19I2 is equal to 1. Now we will solve these two equations. Then what is the solution of these equations? So there is nothing to solve. So now this is equation 1, this is equation 2. By adding or subtraction, we are not getting any solution. That's why please transform one equation to the terms of the another equation. So that's why it is better to multiply this equation with 10 and multiply this equation with 9. Therefore, equation 1 into 10, comma, equation 2 into 9. So the equation 1 transforms like this. 90I1 plus 50I2 is equal to 10. Equation 2 transforms 90I1 plus 171I2 is equal to 9. Now I am subtracting 1 from 2. Subtract, subtract, subtract. 90 get cancelled out. 50 minus 171 is minus 121. Minus 121. I2 is equal to 1. Therefore, I2 is equal to minus 1 by 121 amperes. So we got I2. Now we will substitute this I2 value in any equation, then we will get the I1 value. Therefore, substitute I2 in equation 1. So 90I1 plus 50 into what is I2 minus 1 by 121 is equal to 10. For 90I1 minus 50 by 121 is equal to 10. 90I1 is equal to 10 plus 50 by 121. The whole sum is 12. 10 plus 50 by 121 is equal to 90I1. Therefore, I1 is equal to 1260 by 121 into 1 by 90. So this 0 get cancelled. This is 14. Therefore, I1 is equal to 14 by 121 amperes. So we got I2 and I1 values. When these two are connected in this combination where I is equal to I1 plus I2, therefore potential is equal to I into R. Now we are going to find out the potential. Therefore, I1 is equal to 14 by 121 amperes. I2 is equal to minus 1 by 121 amperes. V is equal to I1 plus I2 into R. Because V is equal to IR. So what is I1 plus I2? So it will be 14 by 121 minus 1 by 121 into R is equal to 10 ohms. This is 13 by 121 into 10 ohms is equal to V. Therefore, it is 130 by 121 volts. Therefore, the potential is 1.0744 volts. So 130 by 121, you will get the equation, the value V is equal to 1.0744 volts. This is one of the example how to resolute the current into the multiple directions within a given circuit, and that to be the circuit is complex. Now we are going to discuss about the applications of Kirchhoff's law. First application is Wheatstone Bridge. Bridge means which balances the two ends. So like this. This is one slope, this is one slope. The gap, the connection between these two slopes is a straight line. Means this straight line is balancing these two slopes and the force is due to these two slopes. Like that, in electrical circuits also there are some circuits which are called as bridge circuits. First one is Wheatstone Bridge. This Wheatstone Bridge is an application of Kirchhoff's law. Kirchhoff's law. See, what is the circuit? This is one EMF E, and the current is transferring like this. Let us say if I is the current traveling through the junctions, here it is one junction, it is one junction. Let us write this junction is A, this point is B, this point is D, and this point is C. And what is the application of galvanometer? We are going to discuss all these things. I1 is the current. So I is the current. In this I current, some amount of the current I1 is transferring through this resistor. Let us say this one is R1. Through this resistor, the remaining of the I minus I1 will go to this one. Let us say this is I2. Means I2 is equal to, we can write I minus I1. And this is the loop A, B, D, A. Through galvanometer, one current is flowing, that is said to be IG or I capital G. Next one, this I1 through this, with respect to the junction arm BCDB, the current which passes through this one is I3 and this one is I4. So I1 is through R1, I2 is through R2, I3 is through R3, I4 is through R4. These are the four resistances. With respect to the four resistances which are formed like a loop, with respect to the galvanometer in the middle, this is one loop and this one loop. What is the application of this Wheatstone Bridge? With this help of the circuit, we can find out the unknown resistance which can balance the circuit. The value of the unknown resistance, let us say R1, R2, R3 are the known resistances. To balance the bridge, what must be the resistance of R4? Means how much resistance we should connect in the place of R4. This is the things we can find out with the help of Wheatstone Bridge. So what we can write by the loop rule and junction rule? I1 is equal to I3 and I2 is equal to I4. We can write like this. Let us take two arms. First arm AB, GDA. AB, GDA. What is the Kirchhoff rule we can apply? Minus I1 R1 plus IG plus I2 R2 plus IG plus I2 R2. The sum of all currents or the sum of all potentials around a loop is 0. Means minus I1 R1. What is IG? Minus I1 R1 IG. Whenever the resistances are balanced or the potentials are balanced, there will be no potential difference. That's why current reading in the galvanometer will be 0. What is the use of galvanometer? It is a sensing device which senses the direction of current as well as which can sense the lowest values of the current, means low electric fields. So minus I1 R1 at the time of balancing, IG will be 0 plus I2 R2 is equal to 0. Therefore, minus I1 R1 is equal to minus I2 R2. Therefore, I1 by I2 is equal to R2 by R1. This is equation 1. And we will apply the same Kirchhoff's law rule for the second arm. So second arm, minus I3 R3 plus IG plus I4 R4. Again, the sum of all potentials around a loop is 0. same, minus I3 R3 plus Ig is equal to 0 plus I4 R4 is equal to 0. Therefore, minus I3 R3 is equal to minus I4 R4. Minus minus get cancelled. Therefore, I3 by I4 is equal to R4 by R3. This is equation 2. Before going to see the relations in 1 and 2, there is one condition. We took I1 is equal to I3, I2 is equal to I4. What is the reason? With respect to the junction, I1 is entering and I3 is leaving. And with respect to the junction here, I2 is entering and I4 is leaving. That's why we are saying I1 is equal to I3 and I2 is equal to I4. So, in place of I3 and I4 also we can substitute I1 by I2 is equal to R4 by R3. This is the transformation of the equation 2. So, in equation 1 and equation 2, LHS are equal. So, we can equate the RHS also. So, therefore, it is E1 by L1. Now, I am removing this E1 and connecting this E2, and then the path will become 2, 3, G, N2, A. When it is E2, and now the length will become N2. So, therefore, what is the path again? A, 2, 3, G, N2, A. In this case, again, pi L2, galvanometer reading is 0, minus E2 is equal to 0. Therefore, pi L2 is equal to E2, pi is equal to E2 by L2. This is equation 1, this is equation 2. LHS of both equations are same, that's why we are equating the RHS. E1 by L1 is equal to E2 by L2. Therefore, E1 by E2 is equal to L1 by L2. So, we discussed that R4 is the unknown one. So, now we are going to find out the expression to find out the unknown resistance. Therefore, R4 is equal to R3 into R2 by R1. In this way, we can find out the value of unknown resistance which is in a bridge circuit to balance the circuit in a bridge shape or to balance the Kirchhoff's law in each and every loop. So, for R4 is equal to R3 into R2 by R1. Next, we are going to see one more application of the Kirchhoff law, nothing but the meter bridge. But meter bridge is the simplest form of Wheatstone bridge. Now, we will see the meter bridge. This meter bridge is a simplified form of Wheatstone bridge. Wheatstone bridge. The construction of the Wheatstone bridge is like this. This one, let us write some name. X to Y. This XY is the metal strip, metal wire of 1 meter length. Now, there are 3 metal strips you can see. One metal strip is like this, another metal strip is B, another metal strip is C. A, B, C are metal strips. Metal strips. Now, one known resistance is connected in between the metal strips of A to B, second end of A to the first end of the B. Unknown resistance S is connected in between B and C, second end of B to the first end of C. Now, we are going to find out this unknown resistance. In case of Wheatstone bridges, we have find with respect to the currents and potentials. Here we are going to find out the unknown resistance with respect to the balancing length, because resistance is directly proportional to the length of the wire. So, listen carefully. In between this one, middle point of the B metal strip, we have connected one galvanometer. Galvanometer always gives the direction of current at the same time, which can sense the low electric currents, low fields. So, this galvanometer is connected to this arrow mark. This arrow mark is a jockey, a pen type electrical device. Now we will, after connecting these things, this is one EMF, this is plug key. So now the connection of the circuit was given. Now the direction of current is flowing through all the metal strips and resistors. Now this jockey is moving from X to Y along the metal wires. This known resistance is R, this unknown resistance is S. So whenever this jockey is moving from X to Y at one particular length, means while it is traveling like this, you can see simultaneously we should see the value of the galvanometer. At one particular point, galvanometer needle will be exactly straight. Means jockey is moving correspondingly along the wire, 1 meter square is also fixed. So at one particular length of the metal wire, galvanometer reading will be exactly straight upward. That means there is no current is passing through the galvanometer. At that point, please find out the length. That length is called balancing length. This balancing length, we can say it as L1, is corresponding to the resistance R, because we have moved from here to here, not from here to here. That's why it is resistance R. Now it is meter scale, means 100 centimeters. Let us suppose at 40 centimeters balancing length, galvanometer reading is 0. Why galvanometer reading is 0? Because there is no current. What is the connection between this current to the resistance? V is equal to IR. Therefore I is equal to V by R. When R is equal to infinity, I is equal to 0. So at this particular length, means resistance is directly proportional to length again. So at this particular length or balancing length, R is becoming infinity of the wire, then I is becoming 0. Therefore, this balancing length L1 is to the R resistance. What about the balancing length L2 for the unknown resistance? From the opposite side, then move the jockey towards the R, towards the X. Suppose if it is L1, automatically this point from this end will become 100 minus L1. Therefore, again for S resistance, for S balancing length, will become 100 minus L1, that refers to S. So R by S is equal to, we can write RCM L1 by RCM into 100 minus L1. R and RCM can get cancelled. Therefore, R by S is equal to L1 by 100 minus L1. We should find out the S value. That's why S is equal to R into 100 minus L1 by L1. So the unknown resistance we can find out with a known resistance into 100 minus L1 by L1. This is the way to measure the unknown resistance with the help of meter bridge by balancing the lengths. This is one of the application of Kirchhoff's laws, that is called as potentiometer. This potentiometer is useful in two ways. The first use is which can compare the EMFs. Second use is to compare the internal resistances. What is the construction? The metal strip is folded like this. These two are the balancing lengths. Now this B is the power supply. This R is the variable resistance or rheostat. Power supply. This is rheostat or variable resistance. Plug key. At the point A, these are the two cells, has E1 and E2 EMFs of resistances R1 and R2. And this is the switch box. This E1 cell is connected to 1, E2 cell is connected to 2, 3 is the output. Suppose if you want to find out the balancing length with respect to the first cell, then you should close this path, then the path will be 1, 3. If you want to balance the lengths with respect to the cell E2, then close this path, this one, and the path will be 2, 2, 3. So now one galvanometer is connected which can travel along the metal strip to find out the balancing lengths. First of all, I want to find out the balancing length with respect to the E1, where pi is the potential drop per unit length. So therefore, what is the direction? A13GN1A. One three means I have cut the 2. Means there is no input is given to the 2. I am comparing the EMFs. First place the one cell which is E1 EMF and having internal resistance R1. So A13GN1, this is the loop. Now this galvanometer is moving along the folded strips. So in this direction, what is the equation? Potential drop per unit length is equal to pi. The potential drop into length is equal to EMF. The phi L1 in galvanometer it is 0 minus E1 is equal to 0. Therefore, pi L1 is equal to E1. Pi is equal to E1 by L1. So, ratio of EMFs is directly proportional to the balancing lengths with respect to the positions applied. So, this is the circuit which is useful to compare the EMF of the two cells with the help of potentiometer. Next use of the potentiometer is to balance the internal resistances. This is the circuit to compare the internal resistances of a cell. Here, the circuit is a small change with respect to the previous one. These are all common, K1C and the metal strip which is folded like this, and galvanometer, the balancing length, all are same, but one resistance box is added in place of the first cell, and here one K1 key is present. Now, if this key is open, no current will flow throughout the circuit. In the absence of electric field, in the absence of no current, the potential difference is nothing but the EMF. Whenever key 2 is closed, then current will transfer through the resistance box of with respect to the cell, then it will convert to the terminal potential difference, nothing but the capital V. So, when K1 is open, it converts to EMF. What is EMF? Phi L1. When K1 is open, yes, no current will pass through, then the galvanometer is just simply move on the metal strips at one particular length. It will give the balancing length. That length is L1 in the direction of same AK1GN1A. Now, just close the K1 gate or close the K1 key. Whenever you close the K1, what you will understand, current will pass through it. Then at the ends, we can find out the terminal potential difference. When K1 is closed, if it is closed, what is the direction? AK1 GN2A. It will become terminal potential difference. What is the terminal potential difference? V is equal to pi L2. Therefore, this is equation 1, this is equation 2. E by V is equal to, we will get L1 by L2. Now we are going to find out the ratio of E and V. We will get what is the ratio of the internal resistances. Now we will see the E by V ratio. We know that V is equal to E minus IR. V is equal to IR, therefore E minus IR. From this we can write I into R plus R is equal to E. So, E by V is equal to I into R plus R by IR. I get cancelled. Therefore, E by V is equal to R plus R by R. This R plus R by R is equal to L1 by L2. Now we are going to find out the smaller value. So R plus R by R is equal to L1 by L2. This equation will turn by 1 plus R by R. R is equal to L1 by L2. R by R is equal to L1 by L2 minus 1. Therefore, internal resistance small r is equal to capital R into L1 by L2 minus 1. This is the expression for internal resistance. With this help, we can next in place of E to place another cell of E1 EMF. Then you will get the same equations. Then we can find out the ratio of small r1 by small r2. Like this, we can find out the comparison of internal resistances. These are all the examples and applications of Kirchhoff's laws. Now we will see one problem which relates to the current density and resistivity. The content of the problem is like this. Find the resistivity of a conductor which carries a current of density 2.5 into 10 to the power of 6 ampere per meter square when an electric field of 15 volts per meter is applied across it. Here, if you want to solve this problem, the first step is write down what are the physical quantities given in the problem. We should find out the resistivity which relates to the current density and electric field. What is the current of density in this problem? Conductor carries a current of density 2.5 into 10 to the power of 6 ampere per meter square. That means J is equal to I by A is equal to current density, that is 2.5 into 10 to the power of 6 ampere per meter square. When an electric field of 15 volts per meter, E is equal to electric field, that is 15 volts per meter. These are the two known physical quantities from the problem. What should we find out? Resistivity. Rho is equal to how much? Then try to relate these three physical quantities, J, E, rho. What is the formula? J is equal to rho E. We know that E is equal to rho J. We should find out rho, therefore rho is equal to E by J. Then we should substitute the values. Rho is equal to, what is the E value? 15. What is the J value? 2.5 into 10 to the power of 6. Therefore, 2.5, 15. So we can write it as 150 by 25 into 10 to the power of minus 6. It's 25, 156 times 6 into 10 to the power of minus 6 ohm meter. So this much is the resistivity of a conducting wire where its current density is 2.5 to 10 to the power of 6 ampere per meter square when an electric field of 15 volts per meter is applied across it. Now you will see one problem which relates to the temperature coefficient of resistivity, nothing but alpha. The problem is like this. From this problem we can see some content in it. A silver wire has a resistance of 2.1 ohms at 27.5 degrees Celsius and a resistance of 2.7 ohms at 100 degrees Celsius. Determine the temperature coefficient of resistivity. He is comparing the resistance of a single common wire which is made up of a silver at two different temperatures. At 27.5 it is 2.1 ohms. At 100 degrees Celsius it is 2.7 ohms. Now he is asking what is alpha. Let me write the values. Resistance at T1, where T1 is equal to 27.5 degrees Celsius. What is resistance at T1? 2.1 ohms. Same like resistance at T2 is equal to 2.7 ohms. So what is T2? 100 degrees Celsius. Now he is asking alpha. The formula which relates resistance and alpha is RT2 is equal to RT1 into 1 plus alpha into T2 minus T1. Resistance at T2 temperature is equal to resistance at T1 temperature into 1 plus alpha into T2 minus T1. What is the standard formula for this situation? R capital T is equal to R0 into 1 plus alpha into delta T. We have discussed this formula while I am explaining the theory. Now we will apply the values what we have in the question in this formula. So let us write an equation number 1 for this one. This is the standard formula. We are modifying the standard formula according to the situation given in the question. That is the matter. So what is R at T2? 2.7 ohms. What is R at T1? 2.1 ohms. The 1 plus alpha into, what is T2 minus T1? 100 degrees Celsius minus 27.5 degrees Celsius. Into 1 plus alpha into T2 minus T1, 100 minus 27.5 degrees Celsius. Therefore, 2.7 is equal to 2.1 into 1 plus alpha into 100 minus 27.5 is 72.5 degrees Celsius. 2.7 by 2.1 is equal to 1 plus alpha into 72.5. 2.7 by 2.1 minus 1 is equal to alpha into 72.5. Therefore, alpha is equal to 2.7 by 2.1 minus 1 whole divided by 72.5. We will see the continuation. Therefore, alpha into 72.5 is equal to 2.7 by 2.1 minus 1. It will be 2.7 minus 2.1 by 2.1. Therefore, 0.6 by 2.1, nothing but 6 by 21. This whole is equal to alpha into 72.5. We should find out alpha. Therefore, alpha is equal to 6 by 21 into 1 by 72.5. So 6 by 21 into 1 by 72.5. So what we can write? It is alpha is equal to 6 by 72.5 into 21. The value is like this. So 6 by 21 into 72.5 is 1572.5. So the alpha answer is 0.0038. So what we can write? 0.38 into 10 to the power of minus 2 per degree Celsius. This is alpha. This is the temperature coefficient of resistivity of the given material. What is that material? Silver. Now we will see one problem which relates to the length, area and to the applied voltage whenever some length of the material of the conductor and area it has and how much heat energy it will produce. So which relates the heat energy produced with respect to the length, area and resistivity. So see the problem. There are two wires A and B of same length and same material, have their cross-sectional area in the ratio 1:4. What would be the ratio of heat produced in these wires when the voltage across each is constant? We should find out the ratio of heat. There are two wires A and B of same length. So therefore, just try to visualize the problem. Two wires of same length. What we can write now? LA is equal to LB. So that was over. And same material means rho A is equal to rho B. Its resistivity is also same because of the same material made. Have their cross-sectional area are in the ratio 1:4, but there is a ratio, there is a difference in the cross-sectional area of the material like this. AA by AB is equal to 1/4, or area of the wire A by is to area of the wire B is equal to 1:4. There is a ratio in the areas of the conductor. What would be the ratio of heat produced? Means what we should find out, HA by HB is equal to how much? Or HA is to HB is equal to how much? This is the thing we should find out. When these wires, when the voltage across each is constant, so voltage is also constant. All are same except cross-sectional area of the conductors. In this state, what will be the ratio of heat energies produced in the conductor? We should find out. What is the expression for the heat energies produced by the conductor? Nothing but I square R. According to Ohm's law, we can write I is equal to V by R. Therefore, H is equal to V square by R square into R. Therefore, R and R square get cancelled. So, we will get H is equal to V square by R. Okay, V value is there, but what about the R value? Now, we should convert the R into the given terms of the problem. Nothing but L, rho and remaining terms. So, H is equal to V square by, what is R? Rho L by A. This 1 by A goes up. Now see the problem. LA is equal to LB means L is constant. Rho A is equal to rho B, therefore rho is constant. VA is equal to VB, therefore V square is also constant. So H is directly proportional to A. Because LB is equal to LA, VB is equal to VA, and rho B is equal to rho A. What is H proportional to A means? AA by AB is equal to 1/4. If H is proportional to AA by AB means HA by HB is also 1/4. Or heat energy produced in wire A is to heat energy produced in wire B is equal to 1:4. Now we will see a problem which relates to the EMF and potential gradient. A potentiometer wire is 5 meters long and a potential difference of 6 volts is maintained between its ends. Find the EMF of a cell which balances against a length of 180 centimeters of the potentiometer wire. So the structure of the potentiometer is, its wire length is 5 meters. Let me write L is equal to 5 meters. And potential difference of 6 volts maintained between its ends. Find the EMF of a cell means we should find out the EMF for what is the condition which balances against a length of 180 centimeters of the potentiometer wire. So L is given, V is given. For this much of potential difference, this is the length of the wire of a potentiometer. What should be the EMF when balancing length is 180 centimeters of the potentiometer? So, potential gradient is equal to potential per unit length per unit length. Potential gradient symbol is pi. What is the potential here? 6 volts. What is the length of the wire in the potentiometer? 5 meters. So it is 1.2 volts per meter. Volts per meter. Now, what is the EMF formula? Potential gradient into balancing length. Potential gradient into balancing length. So what is the potential gradient? 1.2 volts per meter into, what is the length? 180 centimeters. That's converted into meters. We will get 1.8 meters. So 1.2 volts per meter into balancing length is 1.8. The answer is 2.16 volts. So 1218 says 216. If you remove the decimals from the back side, it will be 2.16 volts. So this is the EMF of the potentiometer for the balancing length of 180 centimeters. Now we will see one problem which relates to the EMF and internal resistance of a device. A battery of EMF 2.5 volts and internal resistance R is connected in series with a resistor of 45 ohms through an ammeter of resistance 1 ohm. The ammeter reads a current of 50 milliamperes. Calculate the value of R, nothing but the internal resistance. The problem's visualization is like this. There is a battery. EMF of the battery is 2.5 volts. And internal resistance R is connected in series. Means this battery's internal resistance is R. We should find out the R according to the given data. In series with a resistor of 45 ohms. Means resistor is 45 ohms. Through an ammeter of resistance 1 ohm. Means resistance of ammeter is equal to 1 ohm. The ammeter reads a current of 50 milliamperes. Means IA. Means current read by the ammeter is 50 milliamperes. Calculate the R, nothing but the internal resistance. The given question, internal resistance R is connected in series with a resistor 45 through an ammeter of resistance 1 ohm. This means this resistor 45 ohms, ammeter's resistance 1 ohm, and this internal resistance R, these three are connected in series. Therefore, EMF is equal to E is equal to IR. In place of R, we are getting, what is the effective resistance? Or we can write I R effective. What is the R effective resistance? R plus RA plus R. What is the EMF? 2.5 volts. Therefore, let me substitute. 2.5 is equal to, what is the current passing through the ammeter? 50 milliamperes. 50 into 10 power minus 3 amperes into, what is the resistance? 45. What is the resistance through ammeter? 1 ohm. What is R? Internal resistance. So now it will be like this. 2.5 by 50 into 10 power minus 3 is equal to 40 plus 5 plus 1, 46 plus R. So what is this value? This 10 power minus 3 goes up. 2.5 into 10 power 3 by 50. 50, 10 cube, 1000, 50, 1000, 20 times. 1000 in 50 is 20 times. 2.5 into 20, what is the answer? To 20. What is this one? This one is equal to 46 plus R. Therefore, 46 plus R is equal to, what is 2.5 into 20? 50. Therefore, internal resistance is equal to 50 minus 46, 4 ohms. So this is the internal resistance of the cell or a battery of EMF 2.5 volts, which has internal resistance 4 ohms, which is connected in series with a resistor of 45 ohms through an ammeter of resistance 1 ohms. Then it draws the current of 50 milliamperes. Now we will see one problem which is based on the balancing lengths of a meter bridge. In a meter bridge, balance point is found to be at 39.5 centimeters from the end A when the resistor S is of 12.5 ohms. Determine the resistance of R. We know that in meter bridge the known resistance is R and the unknown resistance is R when the resistor S is of 12.5 ohms, means S is 12.5 ohms. The formula for the balancing lengths or balancing points with respect to the given resistances in meter bridge is R by S is equal to L by 100 minus L. We should find out R. We know S, we know L, we know 100 minus L. So what is the L? Balancing length or balancing point. So what is this balancing point? Found to be 39.5 centimeters. So as usual, S is equal to the resistance or which the known resistor, how much? 12.5 ohms. And we know that 100 minus L is equal to, therefore 100 minus 39.5, nothing but 60.5 centimeters. 100 minus 39.5 is 60.5 centimeters. So we should substitute L, S and 100 minus L in the given formula. Then we can get the R value, which is the unknown. Therefore R is equal to L by 100 minus L into S. What is the L value? 39.5. What is 100 minus L? 60.5 into, what is the S value? 12.5. So the answer is like this. Continue. When you calculate all these things, we will get the value of R is 8.16 ohms. Now we will see the problem and its content. The potentiometer arrangement, a cell of EMF 1.25 volts, gives a balance point at 35 centimeters length of the wire. If the cell is replaced by another cell and the balance point shifts to 63 centimeters, what is the EMF of the second cell? He is giving the relationship between the EMFs to the balancing points. So this is the potentiometer arrangement. Cell of EMF is 1.25 volts. 1.25 volts, that is E1. Gives a balance point at 35 centimeters. Corresponding L1 is equal to 35 centimeters. Length of the wire. Means the 100 centimeters is the length of the wire. At 35 centimeters, galvanometer reading shows 0. That is said to be a balancing length. If the cell is replaced by another cell and the balance point shifts to 63 centimeters, means L2 becomes 63 centimeters. What is the EMF of the second cell? E2 is equal to how much? So, relationship between EMFs to the balancing point. So, E1 by E2 is equal to L1 by L2. We should find out E2. That's why E2 by E1 is equal to L2 by L1. So therefore E2 is equal to L2 by L1 into E1. Now we will substitute this L2, L1 and E1 values. Therefore E2 is equal to, what is L2? 63 centimeters. What is L1? 35.0 centimeters. What is E1? 1.25 volts. 63 by 35, as usually 7 is the common, so it will become 9 by 5 into 1.25. So 5, 1.25, we can get 9 into 125 by 50 into 10 into 10, sorry, it is into 100, here also it is into 100. So 1.25 by 5, 125 by 500. This is 4 times 9 by 4 is 2.25 volts. So for this EMF, the balancing length should be 35 and 63 centimeters from the another end. Now we will see one problem which relates to the drift velocity and the different dimensions of the conductor. The number density of free electrons in a copper conductor is 8.5 into 10 to the power of minus 28 meter power minus 3. That is the number density of free electrons. How long does an electron take to drift from one end of a wire 3 meters long to its another end? The area of cross section of the wire is 2 into 10 to the power of minus 6 meters square and it is carrying a current of 3 amperes. First of all, we should write what are the physical quantities that are there in the problem. Number density of free electrons in a copper conductor is number density, N is equal to number density. .5 into 10 to the power of minus 28 meter power minus 3. How long does an electron take to drift from one end of a wire? Means he is asking what is the time taken to drift the electrons from one end of the conductor to the another end of the conductor, where the length of the conductor is 3 meters. From one end to another end is nothing but the length of the conductor. Means L is equal to length of the conductor. This is 3 meters. The area of cross section of the wire is A is equal to area of cross section, area of cross section. How much it is? 2.0 into 10 to the power of minus 6 meters square. And it is carrying a current of 3 amperes. How long does an electron take to drift from one end of a wire 3 meters long? So the time taken for the drift velocity. So how much is the time? We should find out. We know that drift velocity is related to the number density and length of the conductor and area of the conductor and charge of each electron inside the conductor. And we know that time is equal to, drift velocity is equal to length by time, where time is equal to length by drift velocity. By mentioning all these things and after substituting, we will get all the things which is required to solve the problem. So now we will substitute all these values in the given formula, which is sufficient to get the information of the time to take drifting. We know that I is equal to NEAVD. From this expression we can write VD is equal to I by NEA. But time taken for drifting is nothing but L by VD. Therefore, time taken is equal to L by VD. Already VD is I by NEA. So therefore, time taken for drifting is equal to LNEA by I, where L is equal to length of the conductor 3 meters, where N is equal to number density 8.5 into 10 to the power of minus 28, where E is equal to charge of each conductor, nothing but the free electrons, 1.6 into 10 to the power of minus 19 coulombs, where A is equal to area of cross section of the wire, 2.0 into 10 to the power of minus 6 whole divided by I is equal to amount of current 3 amperes. This 3 and 3 get cancelled. So if you multiply all these things, 8.5 into 1.6 into 2 and 10 power minus 28, 10 power minus 19 and 10 to the power of minus 6, we will get the answer like this.